The next project will be presented by Fiona Spuler and Jakob Wessel, and they worked on a project with the title Adjusting Climate Projections. Their ECMWF mentors were Chiara Cagnazzo, Edward Comyn-Platt, and James Varndell. And Chiara and Eddie, they can't join us today, but James is here, and he will give us a short motivational introduction to the project.
So yeah, basically errors or biases in climate models can be caused by all sorts of factors, things like limited spatial resolution, particularly with a lot of global climate models, really large grid cell sizes, simplified physics, or just incomplete understanding of the global climate system. So the use of uncorrected outputs in impact models or climate models can often give unrealistic results. And there are lots of tools for bias adjusting these sorts of things. There's things like ISIMIP, which is quite a commonly used tool in the climate community, but it doesn't really fit in with the sort of software strategy that ECMWF are moving towards, particularly in the CDS, which myself and Eddie and Chiara all work with a lot, the climate data store, Copernicus climate data store, where we want to have a nice workflow for being able to retrieve data in a Python environment, be able to bias adjust that, preferably within a Jupyter Notebook environment, using a nice open source Python package, which Fiona and Jacob have been working on. And yeah, it's very closely aligned with our future software strategy. And I think I'll just let them explain what they've done and show us their lovely ibicus package they've been working on. So, yeah.
No, thank you for the introduction, James. And also at this stage, we want to thank Eddie and Chiara, who can't be here, who are maybe online, but who really gave us excellent supervision and guidance throughout the project. So thank you very much. So we are here to present ibicus. And we've also presented ourselves to you this morning, but for anyone joining online, my name is Fiona. I'm doing a PhD at the University of Reading, and I worked with Jacob, who's doing a PhD at the University of Exeter. And we'll actually spend some time at the beginning motivating bias correction even more, just to sort of motivate why we developed the package the way we did. And then sort of go into the different features of the package, also a small workflow and next steps from our side.
Yeah, why would you be interested in ibicus? Why would you need bias correction? Climate model biases or climate models are super important tools to understand the future state of the climate, prepare for impacts. But even the most advanced climate models in CMIP 6, etc., model biases still exist. A model bias is a systematic difference between the simulated climate statistics and the corresponding real world statistic. It can be a difference in the mean might be a difference for temperature, it can be a difference in some distributional statistic. If you look on the left down there, we see, for example, plotted the distribution of 2-meter temperature for an observed in the climate model. And although they look kind of similar, we see that the climate model has a heavier right tail. And whilst that might not seem like much, on the right-hand side picture, we see the biases in mean summer consecutive maximum hot days, which is a very important index, I think, for heat waves. And we see that in some parts of this climate model explored there are quite substantial biases in Eastern Austria that we might need to remove for doing impact studies. Model biases can be due to a variety of reasons. They can be due to unresolved processes, topography, some kind of interactions, all sorts of things we might be able to control for in our models, but we can't really right now. There are several ways to address model biases. We can, of course, do research for better climate models. This is what's, I think, planned in Destination Earth, for example, as we heard about this morning. But however, research in climate models is quite costly, and we would still like to use state-of-the-art climate models to learn about climate impacts, to do research about how climate change is going to affect us. So one tool that's become quite standard for climate impact studies is so-called bias correction, where we adjust the biases inside the model output. So we don't fix the model substantially or fundamentally, but we try to adjust the output kind of to put it closer to observations. That's done via calibrating kind of an empirical transfer function between the model simulations and the observations to apply this to the future period. We see on the picture on the right, there's one example of a bias correction method where we see the model distribution, we see the observed distribution, and we kind of try to measure them onto each other to correct the model output to make it seem like observations in a reference period and also in a future period.
So that all sounds really nice and really useful, and we've motivated it now and so on. But there's a number of issues with this type of bias correction that we grouped into two categories: fundamental issues and sort of more practical issues that I'll go into because it really motivated what we did in this package. So by fundamental issues, we mean really just limitations of this empirical bias correction after already sort of having a finished climate model. And by practical issues, we mean more the availability of software to actually compare different methods and evaluate their performance in sort of a rigorous way. So fundamental issues, like I said, that means there's some biases in climate models that won't be able, like that empirical bias correction won't be able to correct. So for example, a misplacement of large scale atmospheric circulation, for example, is difficult to sort of match afterwards. And also, as you might have sort of thought, it's quite a sort of ignorant method, so to say. So it just literally matches two distributions at its core. And there's really no sort of inherent understanding of what those two distributions are. So for example, in this paper we cite here, they show that you can essentially match like a bias correct precipitation in Australia with temperature in Germany. I think they showed some absurd example, but what this really means is that you need a good understanding of you need a good sort of selection of your climate model before using it. So if you want to use it for a certain impact study, you have to make sure that sort of in this variable region combination, there's not a bias that will sort of create flaws in your whole project. And also you need an understanding of like a good evaluation of what you're doing with bias correction to understand, does this make sense? Do the results look fine, and so on. However, there's lots of different bias correction methods out there, lots of different academics publishing different things, and they're published sort of mostly in dispersed software packages, some in R, some in Python, some here, some there, and not always sort of with a coherent evaluation framework to go with it. And what I also forgot to mention on the last slide is that sort of this absurd example, you can't really detect that it's absurd if you just do a location-wise evaluation, sort of see if each location looks fine. You have to also look at sort of temporal, spatial, multivariate properties of your climate model, and those type of evaluation frameworks don't really exist. So while we're not really able to address the fundamental limitations of bias correction in the package, we may be able to address some of these more practical issues.
Yeah, this is why we bring you ibicus. It's a flexible and user-friendly toolkit for the bias correction of climate models and associated evaluation. We include in the package 8 peer-reviewed bias correction methodologies covering a total of 12 climatic meteorological variables. To give users the choice of methods, we include an evaluation framework for bias correction, which covers spatial, temporal, multivariate aspects to identify misuse and to help users really find the most suitable method for their use case. And it's flexible, it's easy to use. We operate on numerical levels, so you can integrate with lots of other tools. The package is extendable, and we also took special care that users can adjust each methods according to their needs, according to the impact they want to study. We tested it a lot with ISIMIP 6 and ERA 5 data, so we developed it especially with these data streams in mind. And yeah, it's available on PyPy right now. There's a QR code if anyone wants to scan it, also online. It's available on PyPy. We have a GitHub repo, which is open source under the Apache v2 license. There's quite an extensive documentation on Read the Docs. And we just want to give you a kind of brief overview for the rest of the talk on how the package actually works. There are two main components to it. There's a debiasing component and there's an evaluation component. We wouldn't want to bore you with all the different debiasing methodologies we've implemented. They're quite technical, but just some kind of general differences that debiasing methodologies fall in. there can normally be one difference is whether you do a quantile-specific correction versus an adjustment of mean and variance or other distribution parameters. So if you adjust in the climactic variable, you adjust each quantile individually, or if you just adjust some kind of summary parameters. There can be parametric, non-parametric. So if you assume a special form for the distribution of your climactic variables, you can have different types of trend preservations. For example, we assume that climate change trends in precipitation are normally changes in intensity. So they are multiplicative changes, whilst changes in temperature are normally kind of additive changes. The distribution kind of shifts a bit. There can be a difference in time window. And just these are the methodologies we implemented, just to say ECMWF, which is quite commonly used, is parametric trend preserving quantile mapping, while CDFT is a non-parametric trend preserving quantile mapping. So there are some differences there. Also, for example, ECMWF is implemented as Python software. However, with a interface that's quite difficult to use, but we can show in our package, we can show consistency with the reference implementation, and CDFT is implemented as an R package. What we provide is a unified interface around those.
So implementing those methods from scratch, but sort of in a unified interface. So to the evaluation framework. This is just sort of a table showing what types of properties we can evaluate at the moment. So we can evaluate and maybe just sort of to start with, because what evaluation means is sort of comparing your climate model to the statistical properties of your climate model to observations, and then comparing it again after bias correction. So understanding what has changed. And for that, you need a period where there's where we still have observations. So we split our sort of historical data set into a training and a validation period. And any part of the evaluation is performed on this validation period where we bias correct the climate model. So we have observations compared to raw climate model compared to bias corrected climate model. So we look at some statistical properties. So for example, the bias of the mean or the 5th or 95th percentile, some sort of spatial properties, so spatial correlation within the climate model before and after bias correction, and also sort of the multivariate structure. So the link between temperature and precipitation and whether it still looks the same. Two other things that we look at is trend modification. Like Jacob mentioned, different bias correction methods sort of treat the climate model trend differently. And it has been shown that bias correction can significantly modify the trend of a climate model, which is something you may want to do or may not want to do, depending on whether you consider the trend credible, but which is really important to evaluate, to sort of see, am I introducing some artificial trend here just by applying the bias correction? And then we also implemented a class that we call threshold metrics, because a lot of the impact metrics work via threshold. So this is always a combination of a variable together with a threshold that you can evaluate on all those aspects. So one example would be like frost days. You can look at the number of frost days, look at whether that changes after bias correction, look at the spell length of like dry spell length, or the sort of the spatial and spatial temporal clustering. And sort of just to give you a basket of examples. So here we have two plots where you see the sort of the marginal bias before and after bias correction, and marginal, we mean sort of location-wise, and you can also look at the distribution of this. And here, for example, using CDFT, we looked at the sort of shift in, or the root mean square error of spatial correlation metrics, always comparing observations to the climate model. I'm not sure if you can see this this side, but here we specifically look at two threshold metrics associated with daily maximum temperature. So summer days and icing days. And maybe just to add, there's a sort of pretty commonly used of climate list of climate change indices that is fully integrated in this threshold metrics class. And we actually see here that there's quite a large bias in these two threshold metrics that also gets larger after bias correction. So if you're interested in those metrics and apply this bias correction method, you should not, you should use a different method. So this is why evaluation is important. And here just an example of, for example, the spell length of wet days, where we see that there's one particular method that really sort of extends the wet the wet spell length. So it's really sort of all bias correction is flawed. It's just a matter of correctly evaluating is the sort of philosophy here. And just to take you to through the workflow, so we have one common debiaser class of which all the individual debiasers are child classes of. So you import the debiasers, and then you can initialize the debiasers for a specific variable. And you see here from variable initialization that works via default settings for that specific bias correction method for that variable. So it automatically knows, for example, temperature, you use maybe a normal distribution in that bias correction method or things like that. But also if you, for example, want to try out a beta distribution or something like that, you can customize this. So by using from variable again, but overwriting the distribution as shown below. Okay, this is really not for you to process now. We just wanted to include it because you see the different methods and the different variables, and it crosses wherever there's a default setting. And we put brackets around all the default settings that we basically just made up. So we made them up with informed decisions, obviously, but they're not published anywhere as such, because some publications only look at precipitation, for example. Then after that, you run your bias correction. And as mentioned previously, you need your observational data, your sort of climate model in the period where there also are observations, and your climate model in the application period, which is mostly a future period that you want to bias correct. So you apply the two debiases, and then you evaluate. So what we just want to show here is that you can import sort of predefined threshold metrics, so warm days and cold days. You can calculate and plot all of the different sort of variations you saw in the table. And then you can also, if you're sort of interested in a specific use case, like a specific application, you can say, okay, for example, here we define the 95th percentile of like precipitation over all days of the year as sort of a threshold that you can then look at the spelling, look at the spatial structure and so on.
Yeah, as said, you can download the package from PyPy. Just use pip install ibicus. We're still on a development version right now, but we're planning to put this on a stable version in the next release. There's quite an extensive documentation online on the docs. We have a general overview about the package, how to install it, a brief intro into what is debiasing, and then tutorial notebooks leading through basically everything you would want to do with a package, starting from how to download climate data, how to pre-process data, which falls a bit outside of the package, but we figured it might be nice to include it, getting started, how to adjust debiasers, how to modify different settings, and then an extensive notebook on how to evaluate what are things you might want to look out for. And then also there's the API reference leading you through all the functions that you might want to use, all the classes, providing detailed information about what each debiaser does or does not. And yeah, it's actively, or we're actively maintaining it. We already have the V2 planned, which is going to bring some new exciting features. We can bring or say a few more words about that if there are any questions regarding that. We're super, if you have any feedback, if you want to try out the package, please try it out. If you have any feedback, then please write to us or talk to us directly. And yeah, we had a really great time and have been excited to present that. We have some literature.
Thank you.
Thank you very much.
Are there any questions? Yes.
So you mentioned that any debiasing is basically flawed, and I was wondering, because I imagine there are some cross correlation between several variables. So if you're only debiasing one, you're kind of introducing, and I saw that you mentioned multivariate
evaluation.
Would this kind of take care of that? So kind of, would you notice it if you do it with this multivariate validation, basically?
Yes. So that's the idea. Or yes, that's the general idea. I think there's a large discussion sort of around bias correction, like multivariate bias correction, as well, and whether to sort of to go back to the methods and actually fix it there. At the moment, what we implemented is sort of the evaluations, so that if anything goes wrong, you see it there and you can sort of maybe understand what's going on, understand sort of where's the bias coming from that sort of I'm trying to correct, and that introduces this shift, and then use a different model or use a different bias correction. So that's the idea.
Just to add maybe to that, it's also a question, you can adjust anything into anything. And then the question remains, what do you take from your model and what you want to adjust? And there is a bit of discussion about multivariate bias adjustment. But what we have been following mainly is to say we adjust each variable individually and then want to check afterwards if there are any adjustments to that. So kind of use the physics that the model provides us and use that also as a diagnostic versus kind of the real physics, how it should look, to kind of check whether we inflate anything or whether the climate model actually makes sense in that region, or the precipitation temperature relationship is flawed in itself.
Okay,
Thank you.
Thank you.